Now we will complete our discussion of principal component analysis and tSNE with an example of building models using these variables. So let's start off by loading in the insurance data set. And so we have the data set. Let's just make sure it's been loaded in correctly. And there it all is. Now, what we're going to do is first go and develop principal component analysis, and we're also going to do a tSNE model. So let's first do the principal component analysis, and we're going to use only the continuous variables. So we're not going to use any of the flags. So this is from the previous lecture. We're just going to go copy the data frame into another data frame called DF principal component analysis. Let's get rid of the targets and let us build a principal component analysis. And there we go. Now this is just what we did before. We could do a scree plot real fast. And we're going to use, just eyeballing this, I think we'll use the first 4 principal components. Let us predict using this guy. Let's predict this PCA. And so now we have all of the records have been scored. And you can see that we have, like the first 6 records, we have all 14 principal components. We don't want to use all 14. We just want to use the first 4. So that's what we're going to use. And before we use them, let's go and create a tSNE model. And if you recall from the previous lecture, we like the ones that occurred when the perplexity was 100. So we're going to take this guy and we use the unique command. And let's do that and build our tSNE model. And then I will pause briefly while this runs, and then we will develop the random forest models. So now we know that the tSNE model has completed, and we've copied the 2 tSNE values to our data frame. So if I do add DFU, you can see now that we have all of our original data, plus we have TS1 and TS2. But we can't score new data this way. So we have to go and create models to predict these guys. Now, from the previous lecture, we saw that the linear models didn't do a good job, but the random forest did. So let's go and copy, or first create some formulas. So if I type F1, you can see that TS1 is equal to all of our category, our continuous variables, and F2 will be, there we go, that's the TS2 is a function of all of our continuous variables. So let us generate 2 random forests to predict TS1 and TS2. Now these will take some time to execute, so I'm going to stop them. This might take about 5 minutes or so to execute, and that's just a lot of dead air time. So I'm going to pause for a moment, and let's start up again when these finish. So the 2 random forest models are done. So now, if you recall, we have, if we go up a bit, so if we go up a bit, you can see that we have the principal components are done, and those are stored off in DF new. But the point is we have this principal component model. where is it called? PCA2. So we got that guy. And we also have 2 random forest models that will predict our tSNE model. So we have everything we need to add these to our data set. So let's do that now. So what we're going to want to do is first, let's build models using only the original data so we can see what we're up against. In this case, this is for demonstration purposes only. We're only going to build a flag model or a probability model. So this is, are you going to crash your car? Yes or no. It would work for a linear regression as well, but we're just going to keep it simple. We're going to do a simple yes or no model. So let's take our original data and let's dump him into DF model. That's the one we're going to use. So let's take that guy and let's get rid of the amount. We don't want him. And let's just, this is what we have. So this is the data we're going to use. We're going to predict the flag. Did the person crash their car? And we've got all of this original data and all the flag data and everything. So that's what we have. This is what we've been working with all, in all the other videos. So let's develop a couple of decision trees first. We're going to use one that has a Gini splitting rule and one using an entropy information rule. So we'll do that real fast. We're going to go as much as 10 levels deep, and we're going to calculate the flag using all of the variables. So let's do that real fast. And then we're going to, once that's done, we will display the Gini coefficient model. And there it is right there. Let's expand it a little. Okay, there it is. So again, the oldest claim, in other words, if I have a recent claim, if I haven't spent a lot to fix your car in the past, you're probably not going to crash your car. So the probability goes down from 27% to 18%. Your job, traffic tickets, things of that nature. So this is all common, all familiar stuff we've used before. Let's also do a, I believe that was the R plot. Let's use that one here. I think that was, this one is the entropy here. And this is, do you drive around in the city or the country? If you go in the country, you don't crash your car, your job, your home value. So this is the stuff that makes you crash your car if you're using entropy. So we have a Gini coefficient tree and an entropy coefficient tree. And now let us look at the variables that are important. Here's what the Gini thought was important. Oldest claim, claim frequency, etc. And here is our importance from the entropy tree. Okay, or do you drive around in the city or the country? Type of job you have, things like that. So this is, again, this is relatively familiar stuff. Now we're also going to do a logistic regression model. So we're going to use a forward selection to decide what variables are important. And again, from previous lectures, we understand that we have to first create a model using everybody. And then we're going to use one using just the intercept, so no variables at all. So let's do that real fast. Both of those are finished. And using these two variables, we're going to do a stepwise selection. And we're going to say, start with nothing and keep adding variables one at a time until you use up to, find the best model using nothing to everything. So let's do that. And here we go. So the first thing it did was it found urban, then salary, job, MVR points, license revoked, minivan, kids drive. It keeps adding variables, and if you watch, our AIC value continues to get lower because the AIC is you want as low a value as is possible. So it keeps adding variables, type of education you have, etc. So this should be done in a few minutes. And down to 92, 63. Just added the number of people on the policy. And we're getting close to finishing. Well, maybe not. Oh, there we go. So now we're done. And we have, this is our best model right here. So this is the model. Now what we will do is we will do a ROC curve. And we will also plot the ROC curve and print the area under the ROC curve. So this is not using principal component analysis. We're not going to use the tSNE. This is just raw data. So you can see our Gini tree, not a real good tree here. Here's our entropy tree, a little better. This is our logistic model, very nice. And here is our area under the ROC curve. So let's take a screenshot of that real fast. And whoops, I'll have to bring that up. I'll pause for a minute. Okay, so here's the snipping tool. Let's just take a quick screenshot of this thing. So we're going to use that for comparison purposes. So that's the one we're trying to beat. This is what we currently have without the principal components or the tSNE. So let's put that off to the side. And now we're going to come over here and let's load our data frame in. Again, let's get rid of the amount because we don't want that. So if I do head here, head df model, and there it is. We got that guy right there. Now let's come over here and let us put our principal components into it. So if we do head df model, there it is. All the original data is there, plus we got our principal components. Now remember, we only needed 4 principal components, but also let's see if our tSNE variables are any good. So remember, we have to use our random forest to approximate that. So let's add those guys. Okay, so if I do head d data frame model. So now we've got all of our original variables, plus we've got our principal components and our tSNE models, tSNE. Okay, but if we got these guys, they're all basically just these guys all combined. So let's get rid of our original variables. Not all of them. We didn't use the flag, so we're not going to use those. But let's get rid of our kids drive home. All of our continuous variables, they're going to be gone. We're not going to use those. Because if our principal components are any good, or if these guys are any good, they should be a substitute for all of those 14 variables. So they're gone now. We're not going to use them. So now we will first try to do a Gini decision tree and an entropy decision tree, and let's print off the Gini tree first. And so here's our Gini decision tree. And this is going to say, do you live in the city or the country? Then, this is the first variable. And then it says principal component 1. So the principal component is clearly a predictive variable. And then, that's about all it is for the Gini. So principal component 1 was the only one it used. What about our friend, the entropy tree? Let's take a look at that. Let's see if that used any of our principal components. That one used principal component 1 again, principal component 1, principal component. So this guy, both of these guys use principal components to 1 and 2. They both made it into the model. Let's take a look at the regression. So let's see what's important. Let's see what the tree considers to be important. Principal component 1. Oh, TS. So the tSNE model variable was considered important. So the tree actually liked a lot of this stuff, but the ones that made it into the model are 1 and 2. Okay. Now let's see. Now let us develop an upper model using everybody, and then we're going to use this guy using nobody, and then we're going to use a forward selection. So let's do that real fast. So what made it into the model? Principal component 1 made it into the model. Principal component 4 makes it into the model. A couple of the flag variables are making in. Principal component 2 is in there. Anybody else making it? Oh, tSNE variable made it in. Keep going. And there it is. Look at that. 1, 2, 3 of the principal components and 1 of the tSNE model variables made it in there. Okay, now let's see how well these guys did. So we first look at the trees. Look at that. Both of the rock curves. Now let's see what we're up against. Let's see the rock curve. This was the rock curve before we did any of the, before we did any of the principal component analysis. It was a pretty, certainly the regression did an okay job, but the trees were, Now if we come over here to the side, you can see the area under the rock curve, 67, 72, and 81. Let's see how things went with once we use principal component analysis. (74, 75, and 80, almost 81. So definitely both trees got better, and the regression stayed about the same. Lost just a fraction of accuracy, but that could just be random noise. But clearly, using the principal component analysis has, in some cases, improved things, but you can't always count on that getting better. So don't take this as it's always going to get better. But the takeaway from this is that when you do use principal component analysis and or tSNE, you can take a lot of variables and reduce it to a few variables and not lose any serious accuracy. So this is a great way of reducing variables. So that concludes our discussion of principal component analysis and tNSE, or I keep saying it wrong. Here it is, R tSNE. So if you're going to, tSNE is the technique, but if you're going to do it in R, this is the library, R tSNE. So anyways, that concludes our discussion.